Hi students, a very good morning. In this class, the second application of Biot-Savart law we are going to discuss. So the first application was the magnetic field due to a straight current carrying wire, and so many sub applications and numericals we had discussed on that topic. Now look at here, the magnetic field due to a current carrying circular coil. What is this? The magnetic field due to a current carrying circular coil. It's not a straight current carrying wire. It is a circular coil. And how the circular coil is, I just wanted to show you, and look at this carefully. And this is the circular coil. A current I is flowing through this circular wire. Look at here, the current I. So the clockwise or anti-clockwise the direction of current is. Tell me, the direction of the current is anti-clockwise direction. Okay, so I'm writing the same here. So the current is moving in anti-clockwise direction. Okay, so now what is our aim? Let's see. The magnetic field due to this current carrying circular coil at the center we need to find out by using Biot-Savart law. Okay, so this I am writing here. So this is the second application. The second application of Biot-Savart law. Second application of Biot-Savart law. This is, you know, the radius of this, carefully see, you know, the radius of this is R. Okay, so let us take, according to Biot-Savart law, I am writing here, so dB bar is equal to, I am writing in the vector form, dB bar is equal to mu naught by 4 pi I dl bar cross R bar divided by R cube. I hope you could recollect the vector form of Biot-Savart law. So dB bar is equal to this much. So what is dl bar and R bar? That's most important here. What is dl bar? So dl bar is a small length element through which the current is flowing. So let me take a small length element through which the current is flowing. See, this is what a small length element through which the current is flowing. And the current element is IDL. Okay, so I'm writing here. So somewhere I can write here. So IDL bar is equal to current element. So what is the current element direction here? So current element direction is in the direction of DL bar or in the direction of current. So you can say this is what your DL bar direction or IDL bar direction. Okay, now, and this is what ideal bar, and it's a point O. At this point O, due to this ideal bar or due to this small length element through which the current is flowing, the magnetic field at this point will be dB bar. dB bar is what? Because of the small length dl bar. Okay, clear? So now this is dl bar, and where is R bar is here? R bar is perpendicular distance. You have to, sorry, R bar is the distance between the length element and the point of consideration. So this is the point of consideration and this is the length element. So you can say this is R bar. Are you getting the point? R bar. And you know the angle between DL bar and R bar. What is the angle between DL bar and R bar? So this is DL bar and this is R bar. So I am writing here. So angle between them is 90 degrees. Okay. So now let us write one more time. dB bar is equal to mu naught by 4 pi I dl sine theta divided by R cube. This is not the vector form. It is just, what is this? It is not the vector form, it is the magnitude of it. So I into dl into R into sine theta. See, there is R also here. So into R you can write. Okay. So what is sin theta? Here sin 90 degrees, which is 1. So your dB value is equal to mu naught by 4 pi into I dl. Right? Sin 90 is 1 and it is r, and this r and r cancel, r square remain. I dl by r square. Carefully see. So this is the magnitude of, I'm writing here. So this is magnitude of magnetic field. Carefully see. Magnitude of magnetic field at point O due to dl. It's not due to total length. Okay, it's just due to dl. Are you understanding it? Now, what we need, we don't want this small dB. We need the net magnetic field due to this element. If you consider this small element, if you consider this small element, because of this all small elements, there will be some net magnetic field at the center. So that is our aim. So for that, what we need to do? We need to integrate this dB, integrate this expression. Okay. So when we integrate this expression, I'm writing here, so the net magnetic field due to the complete wire B, which is equal to integral dB. Okay, so this integral dB I can write, everything is can be taken out because they are constants. Mu naught, 4 pi, I, r, all are constants, right? So this is the r can also be written as radius of the circular path, right? So no need to get confused, and this I am writing it as small r, so no problem. So here mu naught I by 4 pi r square integral dl. Will you understand? Clear? Are you understanding? So now it's so simple now. So the dl integration mu naught I by 4 pi r square integral dl. What is meant by integral dl? Sum of all the small elements called dl. So what is that? What is that? Integral dl is it the circumference of the circle? Yes, integral dl is 2 pi r, where r is the radius of the circular path. I am writing here. So r is equal to radius of the circular path, radius of the circle. So now here 2 2's are pi cancel, 1 r cancel. So what is remained here? So b is equal to mu naught I by numerator, nothing else is left, by denominator it is 2 and this is not there and it is r. So mu naught I by 2r. Listen to me carefully. This is the magnetic field at the center due to a single circular wire. I am writing here. So this is magnitude of magnetic field due to a coil at O. O is what? At the center of the circular coil, right? So let us concentrate on the direction. This is the most important point. Let's concentrate on direction of the magnetic field at the center only. Okay. So this is the direction you can find by using 3 things. Number 1 is right hand thumb rule. What is that? Right hand thumb rule. So the direction of the magnetic field at the center of the circular coil you can find by using right hand thumb rule, and second thing is by using the reverse of the same right hand thumb rule, and the third one is the most important, which is called clock face rule. Clock face rule. So this is what we will be discussing now. Number 1, what is right hand thumb rule? I have told you already. Right hand thumb rule is, imagine a straight current carrying conductor is here. If you hold this straight current carrying conductor with your right hand such that the thumb is pointing the direction of current and The curl of the fingers around it will gives you the direction of magnetic field lines. Okay, here also let's understand the same thing. So this is what a circular coil. But to use the right hand thumb rule, you need a straight current carrying wire, but this is a circular coil, right? So no confusion at all. Imagine a small length element. This you can consider as a straight line. A small length element you can consider as a straight line. What is the direction of current? So this is the direction of current. So look at this carefully here. So the direction of current is upwards and we are holding this current carrying wire, and you can see here. So if this is the straight current carrying wire, we are holding like this. So the right side of this, the magnetic field lines are into the plane, and left side of this, the magnetic field lines are out of the plane. Are you understanding? So at this point, so imagine at this point your straight current carrying conductor, you assume. So this is what my right hand and thumb is pointing in the direction of current, and you can see here. So the right side of this current carrying wire means this is the region where the field lines are into the plane, and this is the region means left side of it, the field lines are coming out of the plane. So again, I just wanted to recollect here. So this is the current carrying wire, and if I am holding like this, right side of it, field lines are into the plane, left side of it, field lines are out of the plane. I hope you got the point. Okay, clear? The same thing here. So at this point, if you apply right hand thumb rule, so magnetic field lines inside it and at point O also out of the plane. Are you understanding? So the magnetic field lines are out of the plane, you can see here. So the field lines are out of the plane. Are you understanding the concept? Field lines are out of the plane. Okay, at any point you take here a straight current carrying wire, a small length, and this is what the current direction, and see here right side of this the field lines are into the plane and left side of these field lines are out of the plane. Are you understanding? So this is what the right hand thumb rule. So by using right hand thumb rule, what is the direction of the magnetic field at the center? In this case they are out of the plane. I can write to my final value the magnetic field lines are out of the plane if you write it in the vector form. Got it? Clear? Now a reverse of the right hand thumb rule. So what is the reverse of the right hand thumb rule? I hope you could recollect it. We have already discussed. Reverse of the right hand thumb rule is also true. What is the reverse here? In right hand thumb rule, thumb is giving you current direction. In reverse of it, thumb will gives you the direction of magnetic field lines. Okay. So the reverse of the right hand thumb rule. So thumb will give you the magnetic field direction and the curl of the fingers. Curl of the fingers, you should point the direction of current. So simple. So curl of the fingers, direction of current. You can see here. So we need to keep our curl of the fingers according to the direction of current. See here. So the direction of current in anti-clockwise. You can see here. The direction of current is in anti-clockwise. Direction of current in anti-clockwise. You see the thumb is pointing out of the plane. That indicates the magnetic field lines at the center of the coil is out of the plane. Are you understanding? So magnetic field lines are out of the plane. So this is what reverse of the right hand thumb rule. That is also true here. Clear? So according to the first right hand thumb rule, we got the magnetic field. Reverse of the right hand thumb rule also, we have got the same magnetic field. Okay. Clear? For example, in this case, if the direction of current is clockwise, look at here. If this is the direction of current, see my curl of the fingers in the clockwise I am keeping, and thumb. Thumb is giving you the direction of field lines into the plane. Okay. If the current direction is clockwise, here current direction is anti-clockwise, my thumb is giving you direction of magnetic field lines out of the plane. It's done. Now let's see, the clock face rule is the most important point here, because already we had discussed about right hand thumb rule earlier. So this is the new topic for you called clock face rule. So that's the reason I have given 5 stars here. That much importance is there for this clock face rule. Okay, clear? So what is this clock face rule? Clock phase rule is also used to find the direction of magnetic field due to a circular current carrying coil. Okay, now, alright, start. By seeing the direction of current, we can find the magnetic field lines are coming out of the plane or magnetic field lines are moving into the plane at the center of the coil. Just by seeing the direction of current, we can see that, we can show that, we can prove that, right? How? Let's start. Clock phase rule tells that this is a circle. Imagine this case. So this case current direction is anti-clockwise, and the clockwise direction of current also I am taking from here. So this is the clockwise. Okay, so I am writing here. So current direction is anti-clockwise. Here the current direction is clockwise. Before moving it, so I am just using a small concept here. Carefully see. So there is a bar magnet I am taking here. It's a north pole and south pole. You know, from the north pole, the magnetic field lines will originate. How they originate? Like this. Look at here. Got the point? From the north pole, the magnetic field lines are originating like this. Like this. You can see here. So like this. Like this. What about the south pole? And magnetic field lines are originating from the north pole and they will be moving into the south pole in this way. You can see here. So this is what to the south pole they are entering into. From the north pole they are coming out. You see here also. North pole, the field lines will emerge and they will be moving into the south pole. So by reaching the south pole they will not come to an end. And they will be flowing into the south pole to the north pole. That's called inside the magnet. Okay, I hope it's very clear to you. What we had already discussed is the magnetic field lines forms a closed loop. They start from the north pole and they will move towards the south pole and into the magnet. That means inside the magnet they move from south to north. So that we had already done in the first session of this chapter called moving charges and magnetism. Okay, so now let's come back to our clock phase rule here. Here, according to the right hand thumb rule or reverse of it, magnetic field, here magnetic field lines are out of the plane or into the plane. Tell me, out of the plane or into the plane. So the same diagram I had drawn there, right? So the magnetic field lines are moving out of the plane. Moving out of the plane means from this phase the magnetic field lines are coming out. From this phase the magnetic field lines are coming out. From this phase the magnetic field lines are coming out means this is the particular phase of a coil will behave as a north pole of a bar magnet. I hope you got it. Here magnetic field lines are coming out that indicate this particular phase of the coil will behave as a north pole of a magnet. So that's what I am drawing here. So carefully see in the direction of current I am just drawing. See. Okay. So these two ends if you meet, see the north pole is there. North pole is formed here. Understand? Clear? So north pole indicates the magnetic field lines are coming out of the plane, and this particular phase of the coil behaves as what? You can see here the clockwise direction. If I apply the right hand thumb rule and its reverse, you can see the curl of the fingers are pointing in the direction of current, and you see the thumb is representing the magnetic field lines are into the plane. Into the plane means the magnetic field lines are moving into the plane. So this particular phase will behaves as a south pole of a bar magnet. In this way, you can see, easy to remember. This particular phase of the coil behaves as a south pole of a bar magnet, right? So by using the direction of current, immediately you can tell that here the magnetic field lines are coming out, here the magnetic field lines are moving into the plane. So what I can write finally by using clock phase rule. So if the current direction is anti-clockwise, so the particular phase of the coil behaves as north pole of a bar magnet. Here If the current direction is clockwise, so the particular face of the coil behaves as south pole of a bar magnet. South pole of a bar magnet means where the field lines are moving into, where the field lines are moving out of the plane. So this is what the magnetic field due to a current carrying circular coil. At the center we have discussed. We have discussed about the magnitude first, then about its direction also. Now, so many applications are there. So one by one we will be now discussing. And before moving to the application, listen to me carefully. So this is what the final expression, right? Magnetic field due to a circular current carrying coil at the center, this is the final expression. When there is a single loop, when there is a single loop, when there are n number of loops, okay, when there are n number of loops, this is the coil. Coil can be made up of n number of loops or with a single loop. When there are n number of loops, I can say this is mu naught I by 2 pi r into n. Understand? N is number of turns of the coil, so that I can write a letter. Okay, so just be online. Let's see here. Just now what I had discussed with you is when there are n number of turns in a coil, the magnetic field at the center of the coil is mu naught I n by 2r. It's not 2 pi r. Pi in the numerator and denominator got cancelled while solving the derivation. Okay, clear? So where n is number of turns in the coil. So look at the interesting part of this new expression here. So here magnetic field and the current. When there is more current passing through the coil, magnetic field will be more. When number of turns are more, the magnetic field will be more. When radius of the coil is less, then the magnetic field will be more here. Understand? So B is inversely proportional to R, and you know how the graph represents an inversely proportional, and this is how the graph represents an inversely proportional. So this is B and this is bar R, this is the graph. And B and I, so B is directly proportional to I, and how the graph looks like, so this is B and this is I, you can say they are directly proportional. And sometimes these graphs also were asked in the previous NEET exams. So that's the reason we are discussing here. Okay. Now, one important point from this expression I just wanted to tell you. Imagine you have 1 meter wire of long, 1 meter wire. If this wire is made up into a circular form, so this is what the circle I have got. The circumference of the wire is how much here? 1 meter. For example, the 1 meter wire is made into 5 turns. 5 turns. So then the radius will be decreases. Yes or no? So the radius of this will be decreases. Imagine it is R1. So now it is R2 here. Radius decreases or increases. So definitely it will be decreases. Okay. So when the radius of the coil decreases and number of turns are increases, and definitely it will affect the net value of magnetic field at this point. So in this case the magnetic field at the center of the coil is B1, and in this case the magnetic field at the center of the coil will be B2, right? So from this example what we should understand? We should understand the difference and the relation between number of turns and radius of the coil. Okay, so I'm writing here, so the number of turns, when the number of turns are more, what happened to the magnetic field? So the magnetic field at the center of the coil, right? So magnetic field will be center of the coil will varies. Why it is varying? Because there is a difference in radius of the circular coil. So when number of turns are more, radius of the coil will be decreasing, will be less. So from these 2 points I can say N is inversely proportional to R. So N is inversely proportional to R. I can write N1 by N2 is equal to R2 by R1. Okay. N1 by N2 is equal to R2 by R1. Now, with the help of this expression, the first application we are going to do from the magnetic field due to a circular coil at the center of it. So the first application, look at here, from this hill point. Number 1, the first application. What is the first application? B1 is the magnetic field at the center of the coil when only one turn is there for the coil. When only one turn is there for the coil, B1 is the magnetic field. B2 is the magnetic field when n number of turns. The same coil is made into n number of turns. Magnetic field is B2. Now the question is, the relation among B1, B2 and N you need to find out. So now the application is to find the relation among B1, B2 and N. Are you ready now? B1, B2 and N, right? So let's start. So what I have told you, when n number of turns are changed, definitely the radius of the circular coil is also changing, and how it is varying in this way. So what is our aim here? Relation among B1, B2 and N. So what is B1 and B2? Those are the magnetic field at the middle, at the center of the circular coils through which the current is flowing. So what is our general formula behind that? So B is equal to a mu naught I N divided by 2R. Okay. What are the variables here? So variables are, N is variable because number of turns initially 1. Now second case it is N. R is variable. I have told you already, when number of turns are changing and radius of the coil also will definitely change. When these two are changing, the magnetic field will automatically change. Right? So that is what initial case magnetic field is B1, final case magnetic field is B2. And let's come to the point called I, R and mu naught. And mu naught and I, both are constants, and 2 is also constant. So these three are variables. These three I can write it as B1 by B2, which is equal to N1 by N2, because B and N are directly proportional, into B and R are inversely proportional, that is R2 by R1. Alright. So now it is B1 by B2 is equal to N1 by N2. I am writing here N1 by N2 into R2 by R1. You can write in terms of N. Why? Because we need to find the relation only among B1, B2 and N. So there is no point is given about R. So that's the reason in terms of N everything must be there. So that indicates this R2 by R1 value we can find from here in terms of N. See here, R2 by R1 is N1 by N2. So the same thing I am writing here, N1 by N2. N1 by N2 into N1 by N2. Okay, see, R2 by R1 is N1 by N2. So from here, B1 by B2 is equal to N1 square by N2 square. Let's come back to this point. B1 is when there is one turn. So N1 is equal to how much? So according to the given data, so I am writing here N1 is equal to 1, N2 is equal to N. Okay, see, B2 N turns. So N2 is 1. So B1 by B2 is equal to N1 is 1, right? So 1 square by N2 square is N square. So B2 cross multiplication, B2 is equal to N square into B1. This is the question asked in one of the previous year NEET exams based on this application. So directly as the application they have asked, which among the following statements is correct according to this application? So this is the correct application. Okay. Now we'll see the second application, then the third application. Let's see the application number 2. In this application, through a circular coil. There's no current is flowing here. So they have just given that there is a charge Q. There is a charge small q is revolving in a circular path. So that's the case is given. With a velocity v, you can see here, with a velocity v, a charge is revolving in a circle. You can see this is the circle through which a charge q is revolving. And you know the radius of the circle is r here. The flow of the charge is nothing but the electric current. So positive charge especially. So the flow of the positive charge is the current. So from here, at the center of the circular coil, you know B is equal to mu naught I by 2R. Here, I they have not mentioned. They have mentioned about charge. So that's the reason I am writing. So mu naught by 2R. So this I can be written as Q by T. What is T here? Time period. Time taken by the charge to complete one revolution. That's called the time period. So B is equal to mu naught Q by 2R. Mu naught Q by 2R into time period is 2 pi R by V. So this is 1 by T, right? So I am writing here. So V by 2 pi R. So that is the time period. Okay. So this is B is equal to mu naught QV divided by, so what is this? 4 pi R square. This is in terms of V. In terms of velocity of the charge. Sometimes the question can be asked in terms of angular velocity, right? So in this case, how you can solve it? So this is one equation in terms of velocity. The same I can write it as mu naught QV divided by 4 pi R into R, because V is equal to R omega we know. From here, V by R is equal to omega. So where is V? So this is V and R. See V by R, you can write omega. So magnetic field is equal to mu naught Q omega divided by 4 pi R. So what is this? The magnetic field at the center of the circular path taken by the charge, which is in terms of angular velocity, right? I have written. In terms of linear velocity, that is V. And sometimes the question can also be asked in terms of frequency, right? Frequency of a revolution. So how to find the frequency of revolution here? So we know omega is equal to 2 pi F. So the same way, mu naught Q into 2 pi F, that's called frequency of revolution, divided by 4 pi R. Pi cancelled and 2 2's. So final expression in terms of frequency of revolution is, what's the numerator here? Remind, mu naught QF. Mu naught QF divided by, so what is denominator remain? 2R. That's it. In this application, 3 different formulas according to the relation between magnetic field and linear velocity, magnetic field and angular velocity, and magnetic field and frequency of revolution we had discussed. Now let's see application number 3. Application number 3 is very important than the other 2, because application number 3 can be combined with your first application of Biot-Savart law called magnetic field due to a straight current carrying wire. I hope you got the point. What I am telling you is, the application number 3, it can be connected with the magnetic field due to a straight current carrying wire in giving higher level numericals, right? So when you go to the JEE mains and advanced level numericals, this application and Biot-Savart law first application will be mixed and questions will be given, and questions will be discussing in the next session. And listen to me carefully, the application number 3, right? So what is this application number 3? So this is a circular current carrying wire. In anti-clockwise, the direction of current is, At the center, the magnetic field is B, and what is that magnetic field value? So the magnetic field value at the center, it is, what is that? It's mu naught I by 2R. It's clear? When this is the angle here, it's 2 pi. When the angle here it is 2 pi, we have got mu naught I by 2R. Now, what is the name of the application? You know, that's the most important point here. So magnetic field, you get here, magnetic field due to an arc, not due to a circle. Some part of the circle we will consider, that's an arc here. Okay, so now B is equal to 2 pi, for example. So what I am taking here is some part of the circle, imagine from here to here. So this is what? Some part of the circle I have taken. So this is the radius of the circle, and this is also radius of the circle at the center. So this is the center of the circular path. So this arc is making an angle theta here. So that may be pi by 3, that may be 2 pi by 3, anything. So that is theta. So there is a current flow is here, I. How the current is flowing in this way. So magnetic field due to the arc through which the current I is flowing at the center. Okay, so that I'm naming at B dash. B dash is the magnetic field we need to find out for the angle theta. Okay, so now just cross multiply, you get the answer. So your B dash is equal to B into theta divided by 2 pi. What is B? B is mu naught I by 2R, right? So mu naught I by 2R into theta by 2 pi. So what is the final expression? B dash is equal to mu naught I by 4 pi R into theta. Look at this. This is the magnetic field due to an arc. The most important application for today's session is this one. Mu naught I by 4 pi R into theta. So many numericals will be solving on this application. Time to time, we will not be deriving it once again. So when the numerical is there, as it is, we will be writing the formula and solving the question, right? So again and again, we are not going to derive it. So listen to me carefully. The B dash is the magnetic field due to an arc through which the current is flowing at the center of the circular path is mu naught I by 4 pi R into theta. Okay. For example, for your better understanding, I'm just writing here. This is the circle you have, right? And this is the circular path which is divided into 4 equal parts here. The circle divided into 4 equal parts. And this arc is making an angle at the center is how much? It's a pi by 2. Yes or no? So this is the arc I am taking here. Carefully see. So this is the arc which is making an angle pi by 2 here. You can see. Right? This is the arc through which current is flowing, and this is pi by 2. And the question is, what is the magnetic field due to this arc at this point called center? So what is that? B is equal to mu naught I by 4 pi R. Look at here. Mu naught I by 4 pi R, where R is radius of this circular path. So this is the radius of the circular path into theta. What is theta here? Angle made by the arc at the center. What is the angle made by the arc at the center? It is clearly given as pi by 2, and this is pi gets cancelled, and B is equal to mu naught I by 8R. So this is magnetic field due to an arc. Okay. First application, second and third application. So look at here. Till now we have discussed, this is the point. At the center of the circular coil through which the current is flowing, the magnetic field is mu naught I by 2R. And you know the direction also how to find it, right? How to find the direction here? By using the clock face rule, you can say the magnetic field lines are out of the plane, as magnetic field intensity is a vector form. So it's a vector. So that's the reason I have written in the vector form. Clear? Now look at this. the magnetic field due to a circular coil at its axial line. Now, you know, this is the origin of the concept. This concept is origin of your mu naught I by 2r expression. How it is an origin of this expression, we'll see now. Imagine you have a circular wire, just a ring. There is a center. From the center, you draw a horizontal line here in this way. So this is the horizontal line in this way. That's called axial line. At any point on the axial line, due to this current carrying ring, the magnetic field we are going to find out. Right? See this. Imagine your ring is this one, so which is having the radius called r. Radius of the circular ring is r. From the center, from the center, so at a distance x, we need to find the magnetic field at the point P here. And this is the point P and this is r. So there is a length here, that is square root r square plus x square. Why? Because of the Pythagoras theorem. At this point P, you know the magnetic field. So that's the interesting part. So imagine the current flowing through this is I. There is a current flowing through this ring is I. And from the axial line, so that means on the axial line at some point P, the magnetic field we are going to find out. And there is a formula for that. B is equal to mu naught I r square divided by 2 into r square plus x square all to the power 3 by 2. Look at here. This is the formula for the magnetic field due to a circular coil at its axial line. So this is the formula, we will be deriving it later. So but we had derived this formula mu naught I by 2r. And what is the topic of now we are discussing is, this is the topic is origin of this formula and how it is true. I'll prove here, listen carefully. So this is the ring. From the center, at some axial point we are finding the magnetic field. Look at the formula. Mu naught I r square divided by 2 into r square plus x square all to the power 3 by 2. And each and every physical quantity you know there. What is this? Mu naught, permeability of free space. I is the current passing through the coil, r is the radius of the coil, and 2 r is the radius of the coil, and x is the distance between the center and the point P, which is along the axial line. Okay, now come back to the diagram here. So this is the circular current carrying coil. From here, the point P is here on the axial line somewhere. Okay, now at the center, the magnetic field we have mu naught I by 2r. At the center means the x is not taken on the axial line. So this x is kept on the center point. Understand? So when x is equal to 0, so that means the magnetic field will be at the center we will be finding. So I am writing here at the center. That indicates x is equal to 0. When x is equal to 0, magnetic field due to this current carrying coil at the center will come. So that will be B suffix center is equal to mu naught I r square divided by, what is that? 2 into r square x square, that will be 0. R square all to the power 3 by 2. And you see 2 cancel here. And what is remain? R cube is remain. And this is r square. R square by r cube. This r square and r square cancels. R remains here. So magnetic field at the center, which is equal to mu naught I by 2r. See, this is the expression similar to this. Here we have taken small r is the radius of the circle. Here capital R is the radius of the circle. There is no difference here. And the direction you can find according to the right hand thumb rule or reverse of the right hand thumb rule, or finally by the help of clock face rule also you can find the direction. So sometimes in NEET exams the question can also be asked from this. So that's the reason I'm giving this expression. This also you need to recollect and practice as maximum as possible. Now It's time to solve the numericals based on this topic and the combination of application of Biot-Savart law. The first application and the second application we will be doing in the next class.